Welcome to the session on trigonometry and modelling, review exercises. The objectives for this session are to review previous topics through exercises, namely, find trigonometric ratios of various angles, solve equations involving sine, cos or tan, and prove trigonometric identities. Pause the video and have a go at these review exercises. When you are ready to view the solutions, press play. Before we tackle the first exercise, let's recap some theory. One of the most common measures of angles is in degrees. 1 degree equals 1 out of 360 of a revolution or a circle. Angles can also be measured in radians. Pi radians equals 180 degrees. We're now going to find trig ratios using an equilateral triangle. Consider the triangle ABC shown on your screen. This is an equilateral triangle of side length 2 centimeters or 2 units. Each angle is 60 degrees. If we drop a perpendicular from A to D as shown, the length BD is 1 centimeter or 1 unit, and the angle BAD is 30 degrees. We can now use this triangle to find various trig ratios. Notice also that the length AD is equal to √3 by Pythagoras. We also remind ourselves of some important angles in radians. 30 degrees equals pi by 6 radians, 60 degrees equals pi by 3 radians, and 45 degrees equals pi by 4 radians. So here's 60 degrees or pi by 3 radians in our triangle, and here's 30 degrees or pi by 6 radians. We are now ready to tackle the first exercise. We're going to use the formula sine B equals opposite over hypotenuse. So let's solve exercise 1a. Sine pi by 3 or sine 60 degrees equals opposite over hypotenuse. So here's the angle B, sine pi by 3. Here's the opposite, which is equal to √3, and here's the hypotenuse, which is equal to 2. So sine pi by 3 equals √3 over 2. And now for part B. We're required to find cos pi by 6. The formula for cos A, or cos of an angle, is equal to adjacent over hypotenuse. So let's plug these values into the formula. And so we have cos pi by 6 equals the adjacent, which is √3, over the hypotenuse, which is equal to 2. So cos pi by 6 equals √3 over 2. In order to tackle part C, we're going to use an isosceles right-angled triangle, as shown on your screen. In particular, we're going to use the formula for sine, since we're required to find sine 45 degrees. So let's solve part C. Sine 45 degrees equals the opposite, which is equal to 1 in this example, over √2, which is equal to the hypotenuse. So sine 45 degrees equals 1 over √2. Before considering exercise 2, let's take a look at some more theory. Solving quadratic equations in sine theta, cos theta or tan theta may give rise to two sets of solutions. So for example, consider the equation 6 cos squared x minus cos x minus 2 equals 0. Factorising gives us 2 cos x plus 1 times 3 cos x minus 2 equals 0. Then setting each factor equal to 0 gives either 2 cos x plus 1 equals 0 or 3 cos x minus 2 equals 0. Let's now take a look at exercise 2 part A. We are required to solve for theta in the interval 0 less than or equal to theta less than or equal to 360 degrees, the equation 10 cos squared theta minus 17 cos theta plus 3 equals 0. So let's solve this. Now 10 cos squared theta minus 17 cos theta plus 3 equals 0 implies 2 cos theta minus 3 times 5 cos theta minus 1 equals 0. Therefore, either cos theta equals 3 over 2 or cos theta equals 1 over 5. Now cos theta equals 3 over 2 has no solutions, since 3 over 2 is greater than 1, and the maximum for cos is 1. So we have to work with cos theta equals 1 over 5. If cos theta equals 1 over 5, the principal value is cos inverse of 1 over 5, which is equal to 78.5 degrees. Now, recall that cos is positive in the first and fourth quadrants, as you can see from the cast diagram. So cos of the angle is either in this quadrant, the first one, as you can see, or the fourth one. So theta equals 78.5 degrees, which is the principal value, or 281.5 degrees, which is 360 degrees minus 78.5 degrees. Now let's take a look at example 1b. Solve for theta in the interval the equation sine squared theta minus 45 degrees equals 1 over 4 for theta between 0 and 360 degrees. So let's solve this. Sine squared of theta minus 45 degrees equals 1 over 4 implies sine of theta minus 45 degrees equals plus or minus a half. So either it's plus a half or minus a half, as you can see. If it's plus a half, then theta minus 45 degrees equals 30 degrees. Sine is positive in the first and second quadrants. So here are the two solutions for this equation. 30 degrees in the first quadrant, or 30 degrees in the second quadrant where sine is positive. But of course in the second quadrant we can't call it 30 degrees. Here's 30 degrees in the first quadrant, and this 30 degrees here is actually 150 degrees in the second quadrant. In other words, 180 minus 30 degrees. Now let's find the other solutions. If sine theta minus 45 degrees equals minus a half, then theta minus 45 degrees equals minus 30 degrees. And sine, remember, is negative in the third and fourth quadrants. We can see this from the cast diagram. Therefore, theta minus 45 degrees equals 330 degrees, which is minus 30 degrees, as you can see, or 210 degrees, which represents this angle here, because sine is negative in this quadrant. And where does 210 degrees come from? It's 180 degrees plus 30 degrees. So the solutions are theta equals 75 degrees, 195 degrees, 375 degrees, and 255 degrees. Notice that we're only looking in the interval from 0 to 360 degrees. Therefore, we rule out 375 degrees because this is greater than 360. So in fact, theta equals 75, 195, or 255 degrees. Before we go on to the next exercise, let's remind ourselves of the definitions of sec, cosec, and cot. So sec equals 1 over cos, cosec equals 1 over sine, and cot equals 1 over tan. Also, we have that since tan equals sine over cos, we have cot equals cos over sine. And at the bottom of your screen, you can see some important identities. Now let's consider exercise 3. Let's take a look at part A first. We are required to prove the identity sec to the power 4 minus tan to the power 4 is identical to sec squared plus tan squared. So let's prove this. Since the left-hand side is the difference of two squares, let's begin with the left-hand side first. And factorize it. As shown. Notice that sec squared in this expression is equal to 1 plus tan squared. So we substitute that. And so we have this expression here. And then tidying up gives us 1 times sec squared theta plus tan squared theta. Which is of course identical to sec squared theta plus tan squared theta, which is identical to the right-hand side of the identity we're trying to prove. And now for part B. We are required to prove the identity 1 minus tan squared all over 1 plus tan squared is identical to 1 minus 2 sine squared. So let's prove this. We're going to begin with the left-hand side and start to simplify it. Notice that 1 plus tan squared is identical to sec squared, so we replace that as shown. And then we split the fractions to give 1 over sec squared minus tan squared over sec squared. Since sec equals 1 over cos, we have that 1 over sec squared is equal to cos squared, as shown. Tan can be re-expressed as sine over cos to give tan squared is identical to sine squared over cos squared. And 1 over sec squared is equal to cos squared, since sec equals 1 over cos. And now we can tidy up. The cos squareds cancel, as shown, to leave us with sine squared. And so we have cos squared minus sine squared. And keeping an eye on what we're trying to prove, let's now replace cos squared with 1 minus sine squared. To give us 1 minus 2 sine squared theta, which is identical to the right-hand side of the expression we were trying to prove. This brings us to the end of this session. If you have understood its contents, you should be able to find trigonometric ratios of various angles, solve equations involving sine, cos, or tan, and prove trigonometric identities. Thank you very much for listening.